So, good morning, everyone. So this is the last session. Indeed, I'm going to speak about two things. So this session is divided into two parts. First of all, I will discuss a little bit about rationality postulates, which is a general method of choosing between options according to desirable properties. So, for instance, this is very common in belief revision, for instance, that there are many revision operators, and how can we choose among them? Yeah. So therefore, there are some postulates. Maybe you know the AGM postulates and postulates like this that help us to choose among different options. And this is also a very common approach in the context of argumentation systems, because we have many options. Okay, so for instance, once we want to tune an argumentation framework, we have many degrees of freedom on what to choose. We can choose different languages. We can choose decide upon the underlying logic according to which we make preference argument. We could, as we saw yesterday, we could define different types of attack rules according to our logic or our intentions. We can decide of different semantics, grounded, preferred, stable, etc., etc. And we can use different aggregations of reasonings. We can use credulous semantics, skeptical semantics. So we have a lot of options here. How can we decide? One way is to use, as I said, the postulates reasoning approach. Okay? This to tune an optimal, so if there is an optimal argumentation framework for a specific need. Okay, so I will divide this discussion or these postulates to several subsets of postulates. The first set will consist of postulates regarding individual extensions, mainly useful for credulous reasoning. The second set of postulates will be about set of extensions. Again, it will be useful for skeptical reasoning. And the last set of postulates will refer to properties of the induced entailment relations. Okay, so let's give a motivation why we need this postulate-based approach. So consider again this argumentation framework based on classical logic. Now we use direct defeat and consistency undercut as our attack rules, and this is the set of assumptions. Okay, so we have these arguments or part of the arguments, and then we get this argumentation framework, and you can check that in this case we have, if I'm not mistaken, three preferred or okay. So again, three preferred and stable extensions. Now, suppose that we want to change instead of direct defeat, remember direct defeat, we attack a specific formula, we change it by defeat. Okay? Once we do this shift from direct defeat to defeat, of course, this has some implication on the argumentation framework. So we get few more attacks, those that are signed by the red arrows. So the red arrows are new attacks by the change from direct defeat to defeat. But what happens now? Suddenly we have another extension which is inconsistent. So by the change from direct defeat to defeat, in this case, we lose consistency of the extensions. So this is a very important property, at least if credulous semantics is considered. We don't want to infer inconsistent conclusions. Okay? So in this case, one might prefer to use direct defeat instead of defeat. Okay, therefore we have to consider different kinds of postulates that will allow us to choose what kind of attacks, logic, etc., we incorporate. Okay, so let me start with rationality postulates for individual extensions. Okay, so we have an argumentation framework, a semantic, a specific extension, and a specific argument, and now we can form a number of postulates. For instance, the first set of postulates are about closure properties of the extension. For instance, the first postulates require that the conclusions of each extension will be closed under transitive closure. The third, for instance, postulate require that there will be closure under a sub-argument. So each extension will be closed under a sub-argument. There are some postulates that refer to consistency, as we saw in the previous slide. So here, this postulate was violated, as you remember, when we shifted from direct attack to attack. So this consistency postulate require that the conclusion of each extension will be a consistent set. Free precedence, for instance, require that each extension will include all the what is called free formulas, all those that are safe, that are in the intersection of the maximally consistent subset. And so every formula that is not involved in any contradiction should be part of any extension. And there is a strong version of this. So instead of subset relation, we switch it by equality. And there are other postulates, exhaustiveness, that we briefly or generally requires that everything that should be in that you want to be that should be in the extension is indeed in the extension. So if any sub argument is in the extension, then we also have its conclusions. We have a strong version of this. Support inclusion is a kind of reflexivity requirement, etc., etc. And obviously there are some relations between these requirements. So this diagram shows that there are some relations about among these postulates. So in this diagram, you see that if a property in the original of the arrow holds, then also the property at the end of the same arrow holds. So this is some here. These are some obvious relations between the postulates. So let's analyze the possible frameworks according to those postulates. For this, recall that we define a general setting. Okay, so first we define the logic, the logic that we want to consider are those that satisfy those in which all these inference rules are admissible. Okay, and remember that we divide the attack rules to three families. Rules that are defined by the attack of the supports, the subset of the supports, so either defeat or undercut. Attack rules that are defined by direct attacks, so either direct defeat or direct undercut, and rules that involve consistency undercut together with some direct attacks. So these are family of frameworks that can be defined in this in our setting, and this diagram or this table, in fact, shows you the general result. So we actually checked each postulate, okay, with respect to each variation. Okay, so you see here are the possibilities of the direct attacks, and here you see which postulates under certain family of attacks is satisfied under which semantics. So for instance, if we look at, for instance, exhaustiveness, so we see that if we, in framework that use direct attacks, exhaustiveness is satisfied with respect to preferred stable and stable and semi-stable semantics. And when we use consistency attack, then exhaustiveness is satisfied with respect to all the semantics, while if you use subset attack, then exhaustiveness is satisfied only with respect to grounded semantics. So altogether, if we try to analyze this, the result in this table, it seems that in terms of a postulate that refer to specific extensions, it seems that direct attacks and consistency attack looks better, behave better than subset attack. But this is only for postulates that that refer to specific, if you are interested in specific extensions. Moreover, note that all these postulates can live together because you see that they are mutually satisfied. For instance, if we take an argumentation framework that is based on consistency attack or direct attack, so at least under grounded semantics, you see that everything is satisfied. So they can live together, all those postulates. Okay, let's consider now another set of postulates. Now we refer to set of extensions. Okay, so these postulates refer, unlike the previous one, refers to set of extensions. So one type of postulates refer to maximal consistency, which means that any extension, according to these postulates, any extension should be induced by some maximally consistent subset of the framework. Here we have a weaker variation of this postulate. Stability requires that the set of stable extension wouldn't be empty, which is not always guaranteed in general abstract argumentation framework. And strong stability requires something a little bit stronger. And here we can see, okay. These are the results regarding these kinds of rationality postulates, and as you can see, in most of the cases, these postulates are satisfied. Okay, let's turn now to the third type of postulates, which refer, maybe the most important one, because they refer to the entailment relations. Okay, and here I will consider two families of postulates. One of them refer to general patterns of non-monotonic reasoning. Okay, so at the 1990s, it was very common to, and later on, of course, it was very common to define different types of non-monotonic logics, default logic, epistemic logics, many kind of logic that based on belief revision, etc., etc. And but it was unclear what are the properties or the logical properties of each kind of logic or type of reasoning. Therefore, there is a very famous work by Krauss, Lehmann, and Megidor that appears here, in which general patterns of non-monotonic consequence relations were set. So they defined three types of families: the cumulative logics, cumulative not in the sense of that we heard this morning, but in the sense of non-monotonic reasoning, cumulative consequence relation, or entailment relation, preferential entailment relation, and rational entailment relations. So let's check them. Cumulativity means that the following 5 properties should be satisfied. First, cautious reflexivity. It's cautious because psi should entail itself. So it's a very cautious version of reflexivity. Right weakening. So let me explain first maybe the setting. So we have a logic, okay, and on top of this, we define a non-monotonic logic, okay, a little bit similar to the what is happening in adaptive logic. Okay, we have the lower limit logic, and on top of this we define higher level logic. Okay, so we have the base logic as usual, according to which we define in context of our argumentation framework, according to which we produce our arguments, and then we have in this case, in our case, for instance, the induced entailments. But in general, Peraslev and Magidor, the KLM, they try to investigate what this entailment relation, what properties should this entailment relation should satisfy, and then again they define different types of families. The cumulative family I referred already to cautious reflexivity. Right weakening means that we can replace conclusion and the conclusion in the right hand side with a weaker conclusion according to the base logic. Left logical equivalence means that we can substitute any formula in the assumptions of our entailment by logically equivalent formula. Cautious monotonicity here, because we are dealing with non-monotonic logic, we don't want to have monotonicity, but we do want to have a cautious version of monotonicity, which means that if we start with specific entailment, so phi follows for S, we can add, psi follows from S, so we can still infer psi from a larger set, so we can add phi to the set of assumptions, but only if phi follows from the other assumptions. Okay, so we have this. We want to jump to this. Monotonicity will allow us to do this always. Cautious monotonicity will allow us to switch from this entailment to that entailment only if phi follows from S. So we cannot add whatever we want to the left-hand side of the entailment relation. Cautious cut is again a weak version of cutting, according to which, for instance, we have note that we have the same set of base set of assumptions in the left-hand side. Okay, and we do the cut over this form. So again, this is a cautious version of standard cut. So entailment relations that satisfy this set of requirements or properties called cumulative. Then there is another family consisting of cumulative entailments which also satisfy the OR rule. So here we also add disjunction. And once we have this property in addition to these properties, we obtain a new family which is called preferential logic. And rational logic are preferential logic together with what we call rational monotonicity. So here is another version of monotonicity, which says that again, so we start with this entailment, and we want to go to that entailment, so to add some assumptions to the left-hand side. And rational monotonicity says that we can do so only if we cannot derive the converse on the negation of what we want to add to the assumption. So we can extend the set of assumptions provided that we cannot derive the counter assumption. This is called rational monotonicity. Okay, and again here is just the table that shows you the result. You just have to check case by case for each possibility, and as you can see, in most cases, cumulativity is preserved. Okay, so we have different entailment relations. Again, each entailment relation is defined by a logic, by attack rules, a type of attack rules, which can be dir, set, or core, and specific semantic, and then we can have a strong skeptical, weak skeptical, and credulous semantics. So we see that all these kind of entailment relations, in most of the cases, they are cumulative. In all the cases where we take grounded semantics, and in some cases when we take other semantics. Well, in less cases we have preferentiality. Here we have to split between the three types of attack rules that are mentioned here. So sometimes we do have preferentiality, but for instance, if we take set attack, we lose preferentiality in all the cases. And rationality is preserved only for direct attack together with grounded semantics. Another interesting property that is shown in this table, that we actually have some entailments that are monotonic. So look at this case. If we take credulous semantics together with preferred stable and semi-stable tank semantics, then we end up with monotonic entailment relation in all the cases where, with respect to all the attacks. Why this is the case? It's a little bit surprising, but here is the claim. The proof is rather simple. Okay. Once we know, remember from yesterday that we know that in order to check this entailment relation, in this case, we can check instead the entailment that is induced by maximally consistent subset. So let's prove it with respect to that entailment, because I've shown you yesterday that in this case that these entailments coincide. Now, with respect to this entailment, it's easy to show that the entailment is indeed monotonic. Let's check, okay? So, if we have this, if we start with this, so psi follow from S according to the credulous semantics with respect to maximally consistent set. What does it mean? That there is some maximally consistent subset of S according to which psi follow from that set. Okay, there is some maximally consistent subset. Therefore, this set remains consistent when we extend the set of assumptions. It might not be maximal anymore, but it is still consistent, right? So there is some maximally consistent set with respect to this enlarged set of assumptions that properly contains or the same as T, so we call it T tag. So there is a maximally consistent subset of the extended set of assumptions that contains the original set. And now, since we found a set that contains the original set, and remember that the entailment relation, the base entailment relation is monotonic, therefore psi still follows from T tag. Okay, it follows from T, but T tag contains T, therefore we still have this entailment since the base logic is monotonic. But once we have found a maximally consistent subset that entails C, we conclude that this entailments hold. So altogether we have here monotonicity with respect to reductions. But once we have skeptical reasoning, then monotonicity of course is lost. It's very simple to see. Consider, for instance, there's a set of assumption P, then P follows from P, but once we add not P to the set of assumptions, it's very easy to see that P doesn't follow anymore from the contradictory solutions, as we saw in the previous section. Okay, how in general we show the other properties, then let me just briefly say that if you want to obtain positive results, then it's easy because we can use the characterization theorem that I've shown you yesterday, that instead of proving everything with respect to argumentation framework, we can in some case switch to the equivalent entailment in terms of consistency, a subset or maximally consistent subset, and prove it there. If we want to obtain negative results, then as usual we provide counterexamples. So for instance, here we see that the strong skeptical entailment satisfy Kasser's cut by switching to the strong skeptical entailment and the weak skeptical entailment satisfying Kasser's cut, because we can show it with respect to the MCS-based entailment. And in order to show that the credulous entailment does not satisfy Kasser's cut, then we can produce some counterexamples. Okay, let's turn to the second set of postulates that according to which we examine entailments, and this set of postulates refer to inconsistency handling. How can we handle inconsistent information in terms of entailment relations based on argumentation systems? So for this, let me establish two simple definitions. So we say that two sets, S1 and S2, are syntactically disjoint, we denote it by this, if they do not have, if there is no shared atomic formula in their language. So the set of atomic formulas of S1 and S2 are disjoint, those sets. And we say that a set is contaminating with respect to a specific entailment relation if for every formula and set S that is disjoint from S, we have that psi follows from F if and only if psi follows from S and S star. This means, in fact, that there is a set S that renders irrelevance with respect to the assumptions. So, for instance, in classical logic, every contradiction is contaminated. Why? Because every S which contains contradiction is contaminating with respect to classical logic. Why this is so? Because one direction we get by monotonicity, and the other direction we get by the fact that everything follows from an inconsistent set. Right? Now we can define several postulates, rationality postulates, that refer to the handling of inconsistent information, specifically in argumentation framework. The first postulate is called conservative consistency. This means that, again, remember that we have a base logic and non-monotonic logic or entailment that is defined on top of this. And we say that this entailment is conservative, preserve conservative consistency if for every consistent set we have the same entailment. Okay, so they coincide with respect to consistent sets. Paraconsistency is a well-established property that was discussed in almost all the course in this school, and in particular we discussed it in detail in the first model. Non-interference and crash resistance are two properties that were defined in the paper by Caminada, Carnielli, and Dunne. Paul Dunne, not Michael Dunne. The Dunne from Dunne Belknap. These are two different Dunnes. Okay, so for instance, crash resistance requires that there will be no contaminating set of formula with respect to the entailment. Okay, and non-interference means that if we have some entailment that's so cipher also from S1 and S2 is irrelevant to S1 and to the conclusion, so we can add it to the set of assumptions. So it doesn't interfere with the original entailment. We can safely add it to the set of assumptions. And again, we can check the properties, and here you have the result, and you can see that in almost all the cases, the handling of postulates that are referred to inconsistency handling, all those postulates, in almost all the cases, these postulates are sets. In some cases, we need to require that the logic is uniform, but that's it. No further requirements. Okay, this is a proof of paraconsistency. I will skip it, and then I will just, for those of you that are interested in this kind of study, there is there are many papers that are related to this topic, also in the context of argumentation systems. So the postulates for logic-based argumentation in general, postulates that are considered specifically in the context of sequent-based argumentation, ABA systems that were mentioned in the second module, a work of Sanjay Mugdil and Harvey Prakan that investigate ASPIC systems with respect to those postulates, etc. So there is a lot of work on this subject. Okay, let me turn to the second part of this talk, and as I promised, we will talk about a little bit about proof methods. Okay, so as usual with non-monotonic systems, proof methods are not simple. The reason is that unlike the standard approach, the standard proof strategy, once we derive something, we might want later on to retract this conclusion or to change our mind because the logic is non-monotonic. So unlike mathematical logic, for instance, we cannot fully rely on everything that we derive. Okay, therefore we need to add to the standard sequent calculi, in our case, some additional machinery that supports this problematic behavior of non-monotonic logic in terms of proof systems. I will just skip the introduction because we have heard about proof system a lot in those other courses, also this course. And let me go directly to proof system for logic-based argumentation, and I will mainly describe here dynamic proof systems. Okay, so what are dynamic sequent calculi? So there are, these calculi are extensions or enhancement of standard sequent calculi together, in our case, with attack rules. Okay, so remember that in order to provide attacks, define attacks, we need attack rules, and then we have to incorporate them also in our sequent calculus. Okay, and as I said, the set of derived formula does not monotonically grow in the size of the set of assumptions. Therefore, derived formulas may be discharged when the derivation progresses. Discharged in the sense that we should treat them cautiously. Okay, maybe later on, discharge formula will become valid again. But we have to take care of those changes of statuses during the derivation. So this means that at any stage of the derivation, a derived sequence may be in at least one of those different statuses. It may be accepted, which means that the sequence is derived from the premises, and there is no known reason to discharge it yet. It may be discharged later on. The second status is that a sequence or an argument may be eliminated. Eliminated means that it is attacked by an accepted sequence. Again, once it is eliminated, this is not the final word. It may be accepted later on. Okay. And the last option is that a sequence may be finally derived. Again, this is a notion taken from, for instance, deductive logics, deductive logic, where this intuitively means that we are confident in the right sequence. Finally, if a sequence is finally accepted, this means that it is accepted, and there is no way to eliminate it in any extension of the derivation. So it is accepted, and it must be kept accepted in every extension of the derivation. There is no way to eliminate it. This induces an entailment relation, of course, which says the following. So psi follows from S. If there is a subset of S, a finite subset, gamma, such that the sequence gamma double arrow psi is finally derived in some derivation in the proof system. Okay, so there is a way to infer, to finally derive in P a sequence whose conclusion is psi. So, again, very generally speaking, we start with some setting. For forming a dynamic derivation, we start with a setting which consists of some underlying logic, monotonic logic, some sound and complete sequent calculus for that logic in order to make derivations of sequence, and a set of attack rules for discharging sequence, for eliminating sequence. Okay? Then we can start with a simple derivation, just producing sequence. Once we have attack rules, we have to reevaluate the statuses of all the sequence. So we should initiate some evaluation process in order to decide what counts as derived. Okay? And by this evaluation, we get a dynamic derivation that preserves the coherence of the simple derivation. So the process is that we keep producing inference and attack rules. Once we apply an attack rules, we have to reevaluate what is happening, what is the status of each sequent in the derivation and accordingly proceed with the derivation. That's the basic idea, and then we have an entailment relation. Before defining the dynamic sequent calculi formally, let me give you some simple and intuitive examples. So let's check it on the intuitive level first. Okay. So suppose that we have classical logic as our base logic, and we take LK, Gensel LK for classical logic, and we now want to use undercut. Remember, undercut means that the conclusion of the attacker is equivalent to some subset of the support of the attacked sequence, as a consequence, the attack sequence is eliminated. Eliminated is marked by this sign. Okay, and the set of the assumptions is P not P2. Let's try to make a derivation now without any definition, just on the intuitive level. Okay, so derivation. So we have a sequence of tuples consisting of the number of the tuple, the derived sequence, and the justification. Okay, so we start with some simple derivation: Q implies Q, P implies P. By introduction of negation on the right hand side, we can move P to the left hand side, to the right hand side, and get not P. And then by introduction of disjunction, we get this tautological sequence in classical logic. Now we can add the other axiom, okay, because it's based on a formula from set, so it's based on not P. And at this stage, we have derived two sequences that are conflicting. Those in number 2, and then the one in number 2 and the one in number 5. Okay, so therefore we must apply an attack rule. For instance, we can form an undercut attack from the sequence in number 5. So this is the attacker on the sequence in number 2. Okay, so this is the attack sequence. So you see that number 5, because of that the conditions here are satisfied, it attacks the sequence in number 2, and as a result, the sequence in tuple number 2 is eliminated. Okay, so at this point, the derived sequence, although it is derived, it should be discharged, because there is an attack by another derived sequence. Okay, let's continue. However, the reverse attack may also be produced, right? Because we can form an attack of the sequence in tuple number 2 on the sequence in tuple number 5 by these new two conditions. So we see that the conclusion of the attacker P implies the negation of the assumption of the condition of the attack form sequence. So P, since P is equivalent to not P in classical logic, then we can form an undercut attack and discharge the sequence in number 5. So now we have in 9 that the tuple number 5 is discharged. Okay, so what should be the status of the sequence at this point? Again, intuitive. Well, we see that P double arrow P and not P double arrow not P, they attack each other, right? So we can initiate attacks of each one of them on the other one. So we do not want them to be finally derived, because we can always produce an extension of the derivation in which one of them is attacked. On the other hand, sequence like this one, which is produced in step 4 of the derivation, should be finally derived. Why? Because according to undercut, there is no way to attack this system. Remember that the undercut attacks are performed on the support of the sequence. And here the support of the sequence is empty. So there is no way to eliminate this tautological sequence. Therefore, in any extensions of this derivation, this sequence will remain accepted. Therefore, we want to have it finally derived. What about Q double arrowed Q? This is the most interesting question here. Well, there are two ways to define it, to attack it. If we want to attack this sequence, we need to derive sequence in which not Q is their conclusions. There are two sequences in this case. P not P implies not Q, and the other sequence is P not Q implies not Q. And sorry, P not PQ implies not Q. In both cases, those attackers of this sequence can be counterattacked by a finally derived sequence. Okay? Because the attackers of this sequence are based on inconsistent assumptions, that sequence, that tautological sequence, counterattack them. But this sequence is already finally derived. Therefore, we can always defend Q double arrow Q. Therefore, the Q double arrow Q should also be finally derived in this case. Yes?
Could not Q double arrow not Q not be an axiom, or what?
No, because not Q is not part of S.
Oh, okay.
All the sequence must be based on S, on our set of assumptions. Okay? Okay, so what we see from this example is that we need an evaluation process for determining the sequence statuses. And this is the whole idea behind the dynamic derivation. That these are simple derivations together with an evaluation process for controlling the derivation. The evaluation process in this case is very simple. You just have to apply a top-down procedure in a very natural way. So what is the idea, for instance, here? Okay, so we start with a derivation. Okay, and we want to evaluate the statuses of the sequence in this derivation. Okay, so we initiate some sets here to be the empty sets. So these are the initialization condition, and then we start to iterate with D. Okay? As long as D is not empty, we do the following. We extract the top sequence of D. Remember, top is the last sequence, the last tuple in D. Okay? And if the last tuple in D is an introduction tuple, okay, so we introduce the new sequence A, then A is added to the derived set. It is also derived in our derivation. If the last sequence is an elimination tuple, so the bar over A means that A is eliminated, then we have to check. In this elimination sequence, there is some other sequence that attacks A. If the attacker is not eliminated, okay, so this is a valid attack, the attacker is an accepted argument, then A, the eliminated sequence, is added to the set of the eliminated sequence, and B is added to the set of the attackers. And then we remove the top tuple and continue with this iteration. And eventually, when the whole derivation is exhausted, then we define that the accepted arguments are those that are derived but not eliminate. And then we return those distance. This is the the evaluation process. So eliminated arguments are those that discharge during the derivation. Attack element, the attack set consists of the attacking sequence, and the accept set consists of the sequence that are accepted. Here is an example. So let's return to our derivation. Okay, remember that we have this derivation with Q, not P, and P. And at this point, we want to reevaluate the statuses of the sequence because here we applied an attack rule. Okay, so we start with the last tuple. At this stage, we see that not P implies not P. This is an eliminated sequence. Okay, and the attacker is sequence number 2. P implies P. The sequence in tuple number. Okay. Okay, then we continue. Okay, we continue with the previous sequence. Okay, 8 and 7. Well, now nothing interesting going on because these are only introductory tuples that there's a sequence, sorry, so you just have to add them to the set of derived sequence. Now, what happens now in tuple number 6? Should we add P double arrow to the set of the attack sequence? Well, the question is no. Why? Because we encounter an attack here. However, we notice that the attacker in this case, the tuple in number 5, is eliminated. So this attack is not really relevant anymore because the attacker is eliminated. So we don't have to do anything here and keep this sequence P double arrow P, we keep it accepted. And in the other cases, we just add the sequence to the set of the right sequence, the right argument, and eventually what we see here that after the evaluation process, we see that at this moment, not P double arrow, not P is eliminated, and all the other sequence in the derivation are accepted. Okay? This is the temporary status of the derivation at this stage. Okay, now a quick definition, how we define dynamic derivation. Yeah.
If you change the order of the sequence, does the outcome change?
Good question. We will have a result that says that at least as long as final derivability is concerned, the order does not matter. So you can have the same finally derived sequence in any order of the derivative. Okay, so dynamic derivation is defined inductively. Okay, so the dynamic derivation D can be just a singleton of a proof tuple, and then by inductive definition, it can be extended by either introducing tuples whose sequence are not eliminated, so we can introduce new tuples that are not eliminated already, or we can apply elimination rules, but we have to be careful, we have to keep the derivation coherent in the sense that at all times the set of attack rules, the intersection of the set of the attack rules together with the elimination rules would be empty. So we don't want to allow any attacker which is at the same time eliminated. Okay, now we can define final derivability. So a sequence is finally derived in a dynamic derivation if it appears in an accepted tuple of the derivation, and the derivation cannot be extended by these items to another derivation in which that tuple is eliminated. In that case, the sequent is finally derived. And now we can define the entailment relation as usual. Okay, so psi follows from S if there is some subset of S according to which this sequent is finally derived. And of course, we are working with respect to a specific setting. Okay, logic, sequent calculus from the logic, and tactics. Okay, back to the running example. Well, now according to the formal definition, indeed, neither P nor not P are not derivable from S. Why? Because P double P and not P and P double arrow P and not P double arrow P attack each other, so they cannot be finally derived. Remember that we have at a certain point situation that not P double arrow P is eliminated. In other stage of the proof, we have the conference situation in which not P double arrow not P is eliminated while P double arrow P is accepted. So we have this kind of situation which, according to which we would not like to accept either P nor not P. Okay, and as I said before, tautological sequence are or tautological formulas that are obtained from tautological sequence are finally derived because they cannot be finally accepted because they cannot be attacked. And concerning Q, so as I said, Q double arrow Q, so sorry, the negation here is a mistake. Q double arrow Q is defended against all the S-based attacker by finally accepted argument, therefore it should also be finally accepted. Let me demonstrate this. Okay, so here we start with a derivation, and then we can produce an attacker, okay, over Q double arrow Q. Here is one of the potential attackers that is based on S. Okay, so we have undercut according to which temporarily Q double arrow Q is eliminated, but then again the tautological sequence in number 4 counter attack this attacker of Q double arrow Q according to undercut. So the attacker is eliminated, and as a consequence, Q double arrow Q is accepted again. But we can produce another potential attacker. Okay? So, but again, this other potential attacker is again counterattacked by the tautological sequence, and eventually all the attackers, all the potential attackers that are based on S, all the potential attackers are eliminated. Therefore, there are no more attackers on Q double arrow Q. Therefore, Q double arrow Q is finally derived. Let's quickly consider another example. Suppose that we have a logic with weak negation, so P should not imply not P, and not P should not imply P. However, the double negation rule on the right-hand side does not hold. Okay, so P does not entail not P, and the attack is by default. Okay, so now suppose that we have this set of assumptions, P, not P, etc., until then the last assumption is for negation before the P. Okay, so let me denote by AY the sequence in which Pi times negation of P imply Pi times negation of P. So for instance, A0 is P implies P, A1 is not P implies not P, etc., etc. let's see what we can derive in this case by using defeat. Okay? So we start with a simple derivation. We can derive A0, P implies P, A1, not P implies not P, A2, not P implies not P. But now you see that there are some attacks between what we have obtained so far. So for instance, since we have A2, A2 can attack A1, okay, but not vice versa, okay? A1 cannot attack A2 because of this rule, but A2 can attack, according to defeat, A1, okay, because the conclusion of A2 implies the negation of the assumption of A1. So accordingly, A1 is eliminated, okay, by the defeat rule. And at this point, A0 and A2 are temporarily accepted. A1 is eliminated. Next, we can derive another tuple, A3, okay, by an axiom. Now, okay, so this is the situation now. We have A3. Once we have A3, A3 can attack A2. Remember, AI plus 1 can attack A1, AI, but not conversely. AI cannot attack AI plus 1. Okay, so A3, the new sequence, can attack A2. Okay? And similarly, A1 can attack A0. So the situation in some sense is reversed. Now, the A's with an even indexes, A0 and A2, are defeated by A3 and A1 respectively. Okay? So we do the process evaluation algorithm, okay, and then accordingly, well, A3 is derived. Note that the attack on A1 is not successful because the attacker A2 is eliminated. Okay, and then we go back. So we have A1 and A0 is attacked. So altogether, now we obtain the sequence with the odd indexes, A1 and A3, while A0 and A2 are eliminated. Finally, we can derive A4. And now the situation is reversed again. Okay, A4 can attack A3. Okay, and similarly, A2 can attack A1. Okay, so as a consequence, we have attacks on, defeat attacks on A3 and A1. And if we do the revision, the process evaluation process, if we initialize this process, we see that, okay, well, we have A4. The attack on A2 is unsuccessful because the A3 was discharged, eliminated. Similarly, the attack on A0 is not successful anymore because the attacker A1 is again eliminated. So we have now A4, A2, and A0 as accepted sequence. But now we reach a stable state. Why? Because A4 becomes finally accepted. Why? The only way to attack A4 is by a sequence with 5 negations. But we don't have such a sequence in S. So there is no way to attack A4 by a sequence that is whose support is based on a subset of S. So A4 is finally derived. Similarly, A4 actually defends A2, okay? Because the only attacker on A2 is A3, and A4 attacks A3. So A2 is, again, finally derived, and for a similar reason, A0 is finally derived. So this is the steady state that we reach, according to which the formulae with an even number of negation are derived, while the formulae with an odd number of negations are not derived. We can represent what is going on in the general derivation. Obviously, this was a very simple one, but we can represent this derivation in terms of argumentation frameworks. Okay, so once we have a derivation, we can represent what is going on by an argumentation framework as follows. So, the set of nodes in the framework consists of all the derived arguments. So if there is a tuple in D in which A is obtained, then A is one of the elements in the graph, in the argumentation framework, and A attack B. So the attack relation in this framework is defined as follows: if there is an application of attack in the derivation by A on B. Okay, so this tuple appears in D, where A is the attacker in the justification. Then this pair AB appears in the attack. Okay, so there is an arrow from A to B in the argumentation framework. So, for instance, in this derivation, the corresponding framework will look like this. And interestingly, we see that the derived element, the derived sequence, are exactly the stable model of the argumentation framework that corresponds to this derivation. So there is a relation between the accepted sequence in the derivation and the stable model of the argumentation framework that is induced by this derivation. Okay, this is what this proposition shows. Okay, finally, let me consider some properties of this entailment relation. Okay, so again, we have a setting, a logic, a sequent calculus for the logic, and attack rules. Let's consider some properties of this entailment relation. Remember that this entailment relation is defined by finally derived sequence. In most of the property will be shown with respect to what we call SAC setting, support attacking and contrapositive settings. So we have SAC setting is a setting in which we pose two requirements. So C admits contraposition, so the contraposition rule is admissible in the sequent, and the attack rules consist only of attacks on the support of the argument. So we can use defeat, consistency undercut, but we cannot use, for instance, rebuttal. Remember that rebuttal is attack with the conclusions of the arguments. And here we insist on, at least in SAC setting, we insist on attack on the support of the argument. Okay, so first note on final acceptability. If A is finally acceptable in D, then it is finally acceptable in any extension of D. This is quite obvious, right? Because if it is not finally accepted, if there is any extension D prime of D in which A is not finally accepted, then since it is not finally accepted, there is another extension, D double prime of D prime, in which A is eliminated. But remember that D double prime is also an extension of D. Therefore, A cannot be finally accepted in D. Okay, so this is quite an obvious proposition. Another proposition is related to the question that I was asked earlier, and it is related to the invariance of proofs. If we have a SAT setting and A is finally accepted in some dynamic derivation D, then any dynamic derivation D prime, for the same set of assumptions, of course, can be extended to the derivation d double prime in which A is finally accepted. So the order does not really matter. Some quick relations between the entailment relation and the base and consequence relation. So one obvious result is if we don't have any attacks, then the relations are actually the same. So this is indeed an extension of the base logic. Similarly, if the set of assumption is conflict-free, then we have again this correspondence between the entailment relation that is induced by P and the base consequence relation. Again, if we have a SAC settings, then in fact the sequent calculus is also weakly complete with respect to the entailment by dynamic derivation. So we have that any tautological sequence that can be derived by C corresponds to the conclusion that can be derived by the dynamic derivation. So there is kind of weak completeness in that respect. Some proposition that is referred to the transitive closure here. Some relation to consistency handling. So the first result is that no contradictory sequence can be finally derived. So we cannot finally derive a sequence whose conclusion is psi and another sequence whose conclusion is not psi. We have, of course, paraconsistent, provided that if the base logic is paraconsistent, then so is the induced entailment by dynamic derivations. We have non-interference in the sense that I described earlier. So we call that this is the definition of non-interference. We have crash resistance as well. So there is no contaminating formula with respect to this entailment relation. What about reasoning with the non-monotonic, the NMR general patterns? Well, we get cumulativity. Remember that this means that all these conditions are satisfied with respect to the entailment that is defined by dynamic derivations. We do not have preferentiality, okay, or is violated. And here is a counter example that can be checked. Another interesting result is the correspondence between the derivation in dynamic, the entailment induced by dynamic derivations and the other entailment that we have considered so far. So remember that we have those. In this setting, okay, so we have classical logic, LK and undercut. So we have this strong skeptical entailment. We saw already that in this case, this entailment is the same as reasoning with maximally consistent subset. So we already know that these four bullets define the same entailment relation, but now we can add another bullet to this set of entailments. It's also the same as the entailment that defined by this thing. So at least in this case, we have this correspondence with respect to strong skeptical entailment. Let me very quickly show you what happens with respect to weak skeptical entailment. So we remember that weak skeptical entailment means that, at least in the case of maximally consistent subset, that Okay, let's okay. This is the more important now. Okay, this is the argumentation-based definition of weak skeptical entailment. Let me recall this definition. Okay, so for every extension, we want that we shall have an argument whose conclusion is psi. Okay, how can we define a corresponding derivation process that describe this kind of entailment? In this case, finally accepted should be weakened. Okay? We say that this consequence is sparsely finally accepted in a derivation if it is accepted, and in any extension of the derivation, there is a sequent that is accepted and has the same conclusion. Okay? Note that in the original definition of final acceptance, we require that the same sequent will be accepted in any extension. Here we require a weakened condition. Any sequent with the same conclusion, not necessarily the same support, should be accepted in any extension. This we call sparsely finally accepted, and accordingly we can define a weaker entailment relation. Why this is weakening is needed? Well, consider this situation. So we have P and Q and not P and Q, and here is a derivation in which you can see, for instance, that, for instance, here the sequence in which Q follows from not P and Q is eliminated, while the other sequence in which Q follows from P and Q is accepted. Well, but we have another situation in which the situation is reversed. So not P and Q does not imply P, while in this time we have that not P and Q implies Q, but while P and Q does not imply Q. Okay, one of them is accepted, the other one is eliminated, but the crucial thing is, in any case, we have one sequence in which Q is the conclusion. So the actual situation is as follows. Neither tuple number 3 nor tuple number 6 is finally derived in this case, because they can be attacked later on. However, their attackers, namely the tuple number 5 and the tuple number 2, they attack each other. Therefore, the attack cannot be applied simultaneously. Okay, so in each stage in the derivation, either we accept this sequent or we accept that sequent. So in each step of the derivation, there is a sequent whose conclusion is Q. Therefore, according to the new definition, Q is sparsely finally derived in this case. Okay, so Q follows according to the weaker definition of final derivability, but it does not follow according to the stronger definition of final derivability. And once we adopt this weaker version, we can have a similar theorem regarding the weak version of skeptical acceptance in argumentation framework. So again, we already know that these entailments are the same, and now we can add to the picture another entailment which is defined by dynamic derivations, and we get a theorem that shows that all those entailments are actually the same. Okay, well, I don't have time to define another version of the system, and so let me just skip to the last slide, which gives some maybe there's some nice pictures about the derivations according to the other option. Okay, so If you are interested in formal proofs in the context of argumentation systems, then you can look at one of these references, one of these papers that use different methodologies or different approach for proof systems. The first one is a survey together with some application about proof system with respect to abstract argumentation. There are some papers about dialogue systems, that are based on proof systems that are based on dialogues, dispute trees in the context of ABA system, game semantics, etc., etc. So there is quite a range of approaches toward proof systems for argumentation frameworks. Okay, let me conclude with few last slides. So just 2 more minutes. Okay, so I suppose that everyone here is convinced that the ability to handle inconsistent information is crucial, and so it's of a primary practical importance. Therefore, paraconsistent should have a key position in practical application. And what I try to show you or to suggest is one platform which might be promising in that direction. But there are other platforms. I try to show some more general approaches, not only with respect to argumentation frameworks, but more generally with respect to AI-based system. So whatever platform you choose, I think that a major challenge for the future is to be able to combine AI-based systems that are capable of analyzing mass inconsistent information, so dealing with mass storage of information, with paraconsistent inference systems that justify the conclusion on a logical basis. So this combination is a real challenge for the paraconsistent. And I hope that some of you will take this challenge as a research subject in the future. So, originally I intended to give 5 models. I managed to describe 3.5 modules. I did not speak about relations to other monotonic formalisms, so there are a lot of translation methods between other approaches to non-monotonic reasoning, for instance, default logic, adaptive logics, logic programming. So there are translation back and forth, sometimes with some restrictions, but interesting translations that in some cases show that argumentation is capable of describing other forms of non-monotonic reasoning. The slides will be on the web, so you can read them together with some, not exhaustive list, but some reference to other papers in which specific translations are applied. A final word, not only that I have not managed to do everything that I planned, even if I were able to present everything, this course is far from being exhaustive. There are many other aspects of handling inconsistency in the context of argumentation framework. For instance, there are papers on argumentation dynamic, in which the argumentation framework may be changed during time. Okay, so attacks may appear or disappear. So argumentation frameworks are dynamic structures. There are some enhancement on the structure of argumentation framework, like bipolar frameworks, in which there are several types of arrows, attack arrows and support arrows, abstract dialectical framework, etc., etc. There is a branch of argumentation framework that is related to probabilistic reasoning. I have not discussed here complexity consideration, but there is a huge amount of literature on that topic, and so on and so forth. Finally, if you want to have some links to more material, or you have questions, suggestions, idea, whatever, this is my email address, and you are most welcome to send the email, and I hope to respond to those emails very quickly. And thank you for it. Everything is clear.
Can I ask a question?
Yeah.
Okay, so these questions, I have two questions. They are philosophical. So the first one is, it is regarding the way that we can define the relation of that between arguments. So, like we have said that an argument that's another argument. Like the conclusion of the first negates the premises of the second, right?
These are some particular cases of attack rules, right?
Yeah, because we
Yeah.
because we have like different, sure, we have different rules. But as I remember, maybe I didn't remember that correctly, but all these rules are somehow focused on the premises of an argument and not. And my question is why? Because, for instance, we can have like that. You can see that in a certain argument, the premises aren't like true or something, but the conclusion still follows. So I was just wondering why this focus on the premises and not on the conclusion.
Okay, so first of all, you are perfectly right. There are attacks that are based on the conclusion. For instance, I've shown in one of the, it was a brief slide that describe an attack that called a rebuttal. Okay, so rebuttal is concentrated on the conclusion. So if the conclusion of the attack sequence is the negation of the conclusion of the attack sequence, then there is a rebuttal between them. But there may be more complicated versions of attack rules on the conclusion. The main reason that we concentrated on attacks on the support sets is that for some reason, maybe we should further investigate this, this rule behaves more properly. So they satisfy more postulates, rationality postulates. So it seems that they are more rational in some aspects, but that's only preliminary results. Maybe it will be interesting to check how would the attacks on the conclusion be.
Yeah, and can I have another question there if nobody has other questions? So I was also wondering, like, since we represented arguments as sequence, and the calculus is classical, right? It's classical. So, but I was wondering, like, why did we choose classical logic? Because since we're talking about arguments, I guess we want to read the implication as sort of because. So the conclusion is because of
Right.
So I'm just wondering, like, why do you think it's better to, maybe for practical reasons, to have classical logic and not, for instance, relevant or intuitionistic? Because there we have like a tighter connection between the antecedent and the postulate, and the because would have more sense. It would make more sense to interpret the implication as because.
Okay, so the immediate response is that the theory allows to use as a base logic other kinds of logic. You don't. Most of the examples were with respect to classical logic. But I show you, for instance, the asparagus puzzle that is based on SPL, right? And as well, we can use paraconsistent logic as the base logic, and intuitionistic logic. It's perfectly fine. So in that respect, we can use a huge variety of logic and languages. You are right that most of the examples that I gave are based on classical logic because these are the most easy example to digest, okay? And in most cases, we use classical logic, but there is no reason to stick to that logic. You just choose your favorite logic, and that's
Ofer, I have a question.
Yeah.
Well, thanks for this very impressive research program. My question concerns the possibility of programming, not only the rules and the derivations, but the winning strategies. You know? Because there are so many rules, so many semantics that, for instance,
Yeah,
suppose I want to choose the best one to win my argument. So how could I try to program a automatic consultant?
good question. There is a jungle of options, right?
Yeah.
But this is the situation in many other areas that you have to choose. So one way of choosing is to use those rationality postulates that guide you what to do. Usually, you at least when you try to adapt to a specific application, usually the base logic is determined. You know what would be your base logic. So at least in that sense, you are usually, the base logic is decided. Of course, there are many other factors that you can play with, right? And so there is no definite answer to your question. It's very application oriented. For instance, I have not shown it, but it appears in the fifth model. If you want, for instance, to represent logic programming, in the concept of Lifshitz semantics, then you would like to use a specific case of argumentation framework. So in some cases, you are guided to the family of argumentation framework that you would like to consider. In other cases, the choice of the specific argumentation is more problematic. You have to sometimes
Because you know, we use Perlog.
Yeah.
You don't have to give it the instructions. Just ask the program, give me please the best way so that I can win. Right?
Yes.
This is famous in logic
Yes.
programming in general, right?
Yeah.
And it could be done.
But in Prolog, many decisions are already made because you know, okay.
Yeah.
Once you
Yes.
have a more degree of freedom, you want to work with relevance logic,
Yeah.
intuitionistic logic, then
You can
Yeah.
program it in Perlog.
that's true.
Not easy.
Not easy.
It's not easy,
Not
but you can.
Yeah.
I think this argumentation framework can be applied to big data. Is it like
It has been applied to big data. In one of the slides, I show you a project in Dundee when they do argument mining. So there is a really huge project, and there are several projects that combine argumentation-based reasoning with machine learning. And in some sense, they are able to, so at least there are some first steps toward this challenge. Okay, to be able to reason properly with mass knowledge. They have some problem in justification, the conclusion, because the machine learning part overrides the argumentation in their application projects. But this is an ongoing project. So there are serious attempts to do this. Yeah. Okay, thank you very much.